Hello. So we have taken a look at the amplitude modulation schemes and how to use analog multipliers to implement them. And now we're going to take a look at the reciprocal operation, which is the demodulation, AM demodulation. An AM demodulator, also known as an AM detector, basically receives an AM modulated signal and extracts the information signal out of it. There are the two most frequent configurations will be the asynchronous detector, which is basically the diode AM detector. It's also referred to as a non-coherent detector. And that basically consists of a diode, which produces half-wave rectification, combined with a low-pass filter, a capacitor. And so the idea is that the input signal arrives. It is an AM modulated signal, and so it has like the high frequency of the carrier signal, and it is modulated in amplitude via the information signal. And so the envelope of that AM modulated signal is what contains the information signal. And so we want to be able to extract that envelope. And so the diode, as I mentioned, provides half-wave rectification, so it eliminates the negative portion of the signal, and then the capacitor charges to the peak, and if we choose the capacitor of the right value, it will not have time to discharge when the signal goes down before the next peak comes along. And so what you will end up with is your envelope or your original modulating signal, with a little bit of high frequency noise because of the charging and discharging of the capacitor. But that's something you can run further through another low-pass filter to eliminate. The other type of AM detector is the multiplier AM detector, which is known as a synchronous detector, and it is a coherent type of detector, meaning it is synchronous. And that one is not as simple as the asynchronous detector. So the asynchronous detector has, has more simplicity. So that's its main advantage, lower cost. It's also a little bit more noisy, so it has worse performance. The multiplier AM detector basically consists of the following. We have our AM modulated signal, which is now the input to the demodulator, the input signal, and it's fed into an analog multiplier, and on the other input of the analog multiplier we apply a carrier signal, our original carrier signal. And when we multiply the two, we get out an output signal, which we can further low-pass filter in order to get our original modulating signal out of the circuit P out. Or perhaps I should call it PM. But anyway, how this happens may be better seen by taking a look at the example that we have been working with. And if we take, for example, the output of our AM modulator, the one with the carrier, we will see it had a component at the carrier frequency of 10 kilohertz, a component at the difference, 10K minus 1K, which was 9K, and a frequency component at the sum. So it had the carrier frequency and the two side bands. And if we multiply that to or times the carrier signal again, which again had a frequency of 10 kilohertz, we can see that as we multiply the carrier signal times each one of those three terms of that modulated signal, we're going to get are the following frequency components. Since I am multiplying two sinusoids in each case, the carrier sinusoid times the sinusoid in the output signal, out of the first product I will get one component at the difference and one component at the sum of the frequencies. The difference will be 0, so that will be at DC. The sum will be 20K, so twice the carrier frequency. As I multiply my carrier signal times the second sinusoid there, I will get two components, one at the difference of frequencies or 1 kilohertz, one at the sum, which is 19 kilohertz. And as far as the last product, one of them is going to be at -1 kilohertz, which I'm going to ignore because it's a negative frequency, and the other one is going to be at 21 kilohertz. So again, notice that I have my original frequency components of my original modulated signal, the DC component, because this was AM modulation, so we had added a DC value, plus the 1 kilohertz, and then the other 3 frequencies are at a much higher frequency and are basically sitting on twice the carrier frequency plus the 2 sidebands, which are at 1K lower and 1K higher than the carrier frequency, because our modulating signal had a frequency of 1K. And so the point here is that it's going to be easy to eliminate those high frequencies if we just run our signal through a low-pass filter. And that's the whole idea behind the coherent AM detector. It's going to have a higher cost associated with it, but as we said, it's going to be more accurate and also less noisy, but also it's possible to use it with all sorts of amplitude modulation schemes, even the ones that we haven't talked about, whereas the diode AM detector only works for certain AM modulation schemes.